All right, everyone, welcome back. This will be our last problem of chapter 3 that we're going to work through. This problem deals with um, binary codes, groups that appear in binary codes. And binary codes are a central tool of modern computer science. Well, I mean, it's maybe not even modern computer science, just computer science full stop. When you want to send some piece of information in a computer, at its most basic level, everything in a computer is zeros and ones. So you can encode your message in binary in zeros and ones and then send it. The issue is that if you're doing this like over radio or the internet or whatever, it can be sometimes received incorrectly. And that'd be a real problem if you were trying to communicate with someone. So we have to deal with this. And modern codes are set up in such a way so that we can tell when an error happens and then fix it. And this is what we're going to start looking at in this problem. So the first thing we have to understand is that since a code is just a symbol of a string of ones and zeros, so simple example, 0, 0, 1, 1, 0, 1, 1. I don't know, just making it up. These are called binary words. Binary because there are only two symbols allowed, 1 and 0. Words because, well, the alphabet in this language is ones and zeros, and so collections of those are called words. Now, we have a definition. If you have two words, A and B, we will oftentimes write these guys as A1, A2, blah, 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 up to AN. All of these symbols, the A's with the subscript I's, are all either 0 or 1. This is just a way of like giving a letter name to a binary string. Then the B's can be B1, B2, B3, right? Another word. Maybe this is the same length. So it also goes up to Bn. Then we're going to introduce something called the error pattern. This is denoted by E, and we write EI. The ith slot will be 0 if they are the same, and 1 if they are different. So the way that you think about this is like checking, right? 0 means no error. They're the same. 1 means there's an error. They're different. So given two strings, A and B, we can check slot by slot, entry by entry. Are they the same or are they different? And in this way, we can come up with an error pattern. There's a little bit of magic here, which is that this is actually very easy to calculate on a computer using the following rule. To add strings together, we define 1 plus 1 equals 0. In other words, this is addition mod 2. And then, with this rule, we can add two things together just slot by slot. Computer scientists would call this bit by bit. So for example, let's make up two strings here. How about 0, 0, 1, 0, 1, 1, 0. And then for B, 0, 0, 1, 1, 0, 1, 0. To form a plus b, we can just do bit by bit adding. So 0 plus 0 mod 2 is 0. 1 plus 1, we define that to be 0. 1 and 0 makes 1. 0 and 1 makes 1. 1 and 1 makes 0. 0 and 0 makes 0. 0 and 0 makes 0. So what does this show? What you see is that when A and B agree, they're in a given slot, or a bit, if you will. Either when you add them up, you get 0 plus 0, which is 0, or you get 1 plus 1, which mod 2 is also 0. So in other words, what we've seen here is that when they're the same, they add up to 0. That's what we saw up here. When they're the same, you get 0. On the other hand, if they're different, you have either 0 plus 1, which is 1, or 1 plus 0, which is 1. And so on the entries where they agree, this one, this one, this one, this one, we get all these zeros. On the entries where they disagree, we get the corresponding ones. So in summary, we can find error patterns by adding bitwise, in other words, slot-wise, and mod 2. So we're saying in our introductory module that groups appear everywhere in nature. I don't know if we necessarily think that computers are nature, but they're certainly part of mathematical nature, right? We see them, we use them all the time in our math classes. Let's think about a couple of properties here. Since this is just normal addition, mod 2, it is certainly associative and commutative. There is a neutral element. The element which does nothing when you add everything together is the string of the correct length of all zeros. Right? When I add a 0 in every slot, nothing ever changes. And there is an inverse. This is a weird way of saying this, but itself, right? Because if the thing we're trying to get, the error pattern of all zeros, that happens when everything agrees. If we agree everywhere in every bit slot, AI equals BI always, then they're just exactly the same. And so every element is its own inverse. Let's take a look at one particular part of this that I think is a little bit surprising. Point 6 in Pinter's book, and then also 7. Pinter says A plus B equals A minus B. He hasn't told us what minus means. He clarifies that this means A plus the inverse of B. When we write it like that, we can start to understand, because this means the inverse of string B. But we just said every element has an inverse, namely itself. B is equal to minus B. So of course this is true. Perhaps even more surprisingly, he tells us that A plus B equals C implies A equals B plus C. How could this be? Algebra in this setting is a little bit weird. We have to keep in mind, what does it mean at every step? The only operation that we have defined is plus and, well, we can subtract because subtracting means adding the inverse. So let's see why this is true. If I take this equation and then I subtract b from both of them, right? I add in b itself. Maybe that's a better way of saying it. That is the same thing as subtracting because b is its own inverse. So these guys cancel, giving the identity element, we could call it 0. And then we said this is also a commutative operation. It's addition mod 2. So A is equal to B plus C. Aren't computers fun?